Good afternoon, everyone. Welcome to the third webinar organized by the Computational Social Science Laboratory. I'm Ho-fung, a co-director of the laboratory. Very pleased to chair today's webinar. It's our distinct pleasure and honor to have Professor Ho-fung Leung here to present to us his research on norm emergence this afternoon. He's an expert in agent-based modeling, and I very much look forward to his presentation. And before his presentation, may I invite Professor Tony Tam, the head of Department of Sociology and also a co-director of the laboratory, to introduce Professor Leung to us. Professor Tam, please.
Yes, thank you, Professor Wang. Welcome, everybody. And good afternoon, Professor Leung. It's my great honor and pleasure to have this opportunity to introduce Professor Leung to this webinar. Professor Leung, I've known him for quite a few years at CUHK. My great pleasure to introduce him, not as a colleague in computer science. Professor Leung is the former chairperson of the department, our distinguished Department of Computer Science and Engineering. And my great distinct pleasure in introducing Professor Leung, whom I call Ho-fung normally, is because he's also my colleague in the Department of Sociology. He has been very kind to be a professor by courtesy in our department. And this begins why I am responsible for introducing Professor Leung. Sociology at CUHK is a major social science discipline in Hong Kong. We are one of the leading departments of sociology in Hong Kong. But for many years after joining CUHK, I've been looking for someone like Professor Leung, who has not just the expertise of computer science, but also have a taste for investigating social phenomena. I was so happy when I ran into Professor Leung a few years ago, knowing that he has spent quite a few years leading a whole team of computer science using AI methodology, applying the technique of multi-agent modeling to social phenomena that we sociologists would like to be able to investigate, but simply do not have the expertise to do so, at least not in a very competent way. So once I learned from Professor Leung, his longstanding work that fits so well as an example of computational social science, I immediately thought he has to give one of the webinar series. And he has done many distinguished work in computer science, artificial intelligence, and so on. But today, we invite him to specifically introduce us to the world of an AI approach to studying norm emergence, the emergence norm in a multi-agent system. So without further ado, I'd like all to join me in welcoming Professor Leung. The floor is yours.
Okay, so thank you, Professor Tam, for the very nice introduction. And it's actually my honor here today to give you a webinar on our research, which I give it a title called Norm Emergence Research in AI. Okay, so I'm pretty sure that some of you would wonder, why norm emergence research in AI have any relation with sociology, right? So this is something that is very interesting, and I hope that after today's webinar, you would find our research interesting and hopefully useful. So let me begin. Okay. So everyone knows that nowadays AI, that is artificial intelligence, is a very hot topic. Right? Everyone talks about big data analytics. Everyone talks about machine learning, but probably there is an active area in AI that's other people, that is people outside AI, do not really, know, that is what we call intelligent agents, okay? Or technically we call this area by the name of autonomous agents and the multi-agent system. So let me first introduce to you what we computer scientists define agents, okay? So basically an intelligent agent is an agent that we say lives in an environment. Okay, so of course, by the name, you know that these agents should have some intelligence. Okay, so by saying that, we mean that an intelligent agent would perceive the environment and then deliberate and then decide what to do. Okay, and of course, the action that the agent decides to perform will have some effect to the environment. And we assume that when agents make decisions, the agent is always rational, right? So the agent would be rational in decision making. And agents will also be sociable with other agents and sometimes even with humans. Okay, so sometimes agents need to interact with human beings. Okay, and also when it performs action, it is both proactive and reactive. Now, what we mean by that is, an agent will be reactive because there will be changes in the environment. So an agent must be reactive to the changes in the environment. And also, an agent is not only purely reactive, it is also proactive because, an agent should have some goals to achieve. So an agent should be proactive in achieving the goals, okay? So when we have many agents in the same environment, then we have a multi-agent system. So our multi-agent system is simply a system in which there are multiple agents. Okay, very simple. Okay, now when there are many agents in the system, of course, they will start to interact, right? Otherwise, it's meaningless to have many different agents just existing in the same environment without any interaction. So we assume that agents in a multi-agent system should interact with one another. Now, when we talk about interaction, of course, we will look at the connection. So, okay, who can interact with whom? So we assume that, okay, they will be connected by some kind of network. Okay, so the most commonly used network topologies in our research would be something like small world networks, okay, or just random networks like that. Or sometimes we can have scale-free networks, right? Because scale-free network has some significance nowadays. Because I guess some researchers has investigated and they found that for many social networks, the topology is actually scale-free. Now, of course, sometimes we assume that there's no network. Okay, so when I say there's no network, that means any agents can interact with any other agents. Okay, so what do we mean by interaction? Now that is a very important question. So when I say this agent interact with the other one, so what do we mean? So in our research in non-emergence, okay, so we usually assume that these two agents play games, okay, in the interaction. Now, when we say games, we mean normal form games. Now, for example, this is one possibility. Now, if you know that, this game is basically a prisoner's dilemma. So for example, here we can assume that these two agents, when they interact, they will play the prisoner's dilemma game. Okay, so this agent will decide, hey, whether I should play C or D, and this agent also would determine, hey, whether I should play C or D, and so on. Okay, so of course, in general, we don't restrict the number of actions to only two, like in this case. So in general, we assume that when agents interact, they will play an N agent to play a normal form game. Okay, so when they interact, they will play an action and then they will get the rewards accordingly, okay, according to the definition of the game. Okay. So now we consider a multi-agent system. So we assume that initially, when the system starts, everyone will have some thoughts, and they think, hey, I would take this action and that action, where I'm interacting with other agents. So for example, this agent will think, hey, I will play A1. This agent will say, hey, I will play A2, and so on. So all these A1, A2, and so on, they are actions available to all these agents, okay? And of course, when they start playing games, when they start interacting with one another, they would learn. Okay, because they will learn that, hey, this action is probably better, right? Or the other action is probably better, even better, and so on. Okay, so as time goes from 1, 2, 3, 4, right? Then every agent learns, and eventually, after some time, we find that all agents would take the same action. Now, when this happens, then we say that a norm has emerged. And this is the reason why we call our research norm emergence research. Okay, so initially, these agents just take some actions arbitrary, right? And after some time, in particular, after they have learned, then they would take probably the same action, okay, like AK, okay, and we call it a norm. Okay, now, what is important here is that every agent learns. Okay, now learning is some kind of intelligent action, right? So because you need intelligence in order to learn, and then we say every agent learns and chooses one same action AK at the end. Now we say this is what we call norm emergence, but remember, it is actually not easy to have everyone playing the same action, right? Because someone would play different action anyway. So usually we only require that most of them, like 90% of them, would choose one same action. Then we consider a norm to have emerged. Okay, that is the convention. Of course, when we are talking about learning, there are many different learning methods. Of course, like in computer science, we are all talking about machine learning. Okay, so there are many different ways these agents can do learning, like Q learning and what we call win or learn fast or Fititious play and so on. So all these are actually names for different learning methodology, right, for agents. And I'm not going to tell you all of them because we just simply do not have time. So I would just give you some idea by telling you the most popular method, that is Q learning. Okay, now by the way, Q is not the abbreviation of anything, because the learning method is simply called Q learning for some reason. Okay, so you will know the reason very soon. Okay, so it's called Q learning. Okay, so we say Q learning is the de facto standard. Okay, so let me tell you, what Q learning is like. Now we assume that there are two agents, and they interact by playing game. Okay, and we assume that they are playing an action normal form game like this. Okay, now when we're talking about normal form games, there's no restriction. So people can use different games for interaction. The most commonly used ones would be like Prisoner's Dilemma, like hot dog games, Battle of the Sexes, coordination, choosing sides, stack hunt. So all these are very common games that people would use, right? There's no restriction. There's no restriction saying that you must use this game or that game, right? So basically we don't care, right? Just use some game. Okay, of course, the results would be a little bit different or very different, but depending on the particular game that you use for interaction. Okay, so no matter what kind of game or which game that you use, basically the idea is very simple. This agent will say, at time t, for example, this is time t, I use an action AK, and by using AK, I get a reward, and my reward is R. So it's always like that, right? I take an action at time t, and then I find that, hey, this is my reward, okay? And then from the reward, I would determine whether the action AK is good or bad or whatever. So by learning, okay? So now, what is Q learning? Now, the main part of Q learning is a set of what we call Q values. Okay, so we assume that we have n actions, like we call them A1, A2 up to AN. Okay, and we say for each action we keep a Q value, which is just a real value. Okay, a real number. So we call it Q of A1, Q of A2. So all these are called Q values. And conceptually, we keep all these Q values in a table. So we call this a Q table. Okay, so these are the Q values and Q tables, and this, there is one Q value for each of the actions. And the agents will learn. Okay, now this is the way they learn. So we say that the Q value of AK at time t+1 will be updated from the Q value of AK at time t by adding this value. Now, what is this value? That's this is the reward he receives. Okay, RT minus QT AK, that is the difference between the current Q value and the reward. Okay, so this Q value will be adjusted. And of course, it will not be adjusted by too much. So this is the learning rate. Okay, so this learning rate is usually between 0 and 1. Of course, if this alpha is 1, right, that is the learning rate is very, very big. Then the Q value will be completely updated by replacing the current Q value with RT, right? Otherwise, this Q value will be just adjusted a little bit, okay, according to the value of alpha. So you imagine these Q values are constantly updated according to the agent's experience, okay? And at a particular time t, the agent will use these Q values to compute the probability of using different actions. So from these Q values, he will say, okay, now these are the Q values. So the probability of my taking A1 in the next time step will be X of A1 and so on. Okay, so I just calculate the probability that of taking a particular action, right, in the next time step. And this will be called the policy. Okay, so the policy at a particular time t is like this for Q learning. That is, usually that is with a very large probability. I will use the action with the largest Q value. Now, because basically the Q value indicates how good the action is. Okay, so I would say, of course, I would take the best action. So I will take the action with the largest Q value. So here we say it exploits the environment. Otherwise, occasionally with very small probability, it will explore the environment. So I just try some other action. Okay, if that's the case, then it will select an arbitrary action to use at t+1. Okay, so. In year 2007, someone studied Q learning, and then it compares the performance of Q learning with some other popular learning methods. So let me introduce briefly, okay, what these two are, right? This is the Q learning that I just introduced to you, right? And then there's a variance called win or learn fast. Well, that is, remember, there's the learning rate. Okay, that's the learning rate. And then, the win or learn fast technique is very simple. That is, when the agent is losing, that is, the current policy or the current Q values are not very good compared with the average policy, then I will increase the value. I will use a larger value for alpha so that I can learn faster. Okay, if I'm winning, then I don't want to change too much. I will use a smaller alpha. Okay, so this is called win or learn fast. Policy hill climbing, but that's part of the name. You can ignore it. Okay, and then fictitious play. Okay, that is another learning method. That is, when I decide what to play with my opponent, I will just look at the history, and if I find that in the history he used different actions with different probabilities, then I assume that when I'm going to interact with him, then the probability of his playing different actions will be will follow this probability, right? So this is called fictitious play. And then in 2007, these people find that by using Q-learning, actually is the best in the sense that when the entire population uses the same learning algorithm, the population of Q-learners, that is agents using Q-learning, are the quickest to evolve a norm. So the Q-learning is the best because by using Q-learning, the norm will emerge the earliest. Okay, so that is the reason why Q-learning has become so popular. Okay, so here I want to point out one thing. Okay, so actually, look at the title. I say social learning versus social learning. Now, actually, in the same paper, 2007. These researchers define social learning as this. Each agent then is learning concurrently over repeated interaction with randomly selected members from the population. That is, each agent will just randomly pick an opponent in the population, all right, and then interact with that agent. And this is called social learning. Now, I know that social learning, right, for example, in psychology would mean something different. Okay, and then this is something that we have to pay attention to because it's very ambiguous because we use many terminologies from social science that will be redefine them. Okay, so we have to be very, very careful when we are talking about different things. Okay, so this is only one example. Now, of course, the other example is reinforcement learning, right? So I understand that reinforcement learning would mean something different, right? In psychology, right? But in computer science, it means some very specific technical algorithm. Okay, so this is something that we have to be very careful. Okay, so we talk about this norm emergence research. What do we do? Now, the norm emergence research aim at improving norm emergence. Okay, so this is the purpose of norm emergence. So you may ask very good questions. So what is improvement? Okay, what do I mean by improving? And how do we improve norm emergence? Okay, so this would be the main topic that I'm going to talk about today, and I will illustrate the idea using some of the works that we have done in the past. So one way of norm emergence research in AI is to change the environmental parameters like learning methods and environment. Okay, so for example, some years ago, okay, in year 2013-15, we consider this method. Okay, that is, we consider a group of agents, a multi-agent system. Of course, they use social learning and they use Q-learning. Okay, and then they also, each agent can also observe a few like M other agents or agent groups. And we investigate, two things. One is, we assume that these agents are learning by individually, okay, individual action learners. That's the name we call them. So we call them individual action learners. So the individual action learners will just learn the goodness of each AI, okay, and then it will select the best action. And there are also joint action learners. Now, for joint action learners, they will not learn the goodness of a particular action, but each of them will learn the goodness of a pair of actions. That is, the learner does not only consider the goodness of AI, but also the action AJ that the opponent is playing. And when it select actions, it will select the best join action. Okay. So of course, this is based on the estimation of what opponent is most likely to play. So this is what we investigate. So we find that when we compare the performance of individual action learning and joint action learning, okay, then we find that joint action learning is actually better. So let me explain to you what we mean by better. Now, so we investigate the performance in climbing games. Okay, this is called the climbing game. So in the climbing game, there is a Nash equilibrium. That's AA. Okay, and of course we will make the results a little bit stochastic. So you see, we change this 7 to 14 or 0. Okay, there is a 0.5 probability of getting 14, another 0.5 probability of getting 0, right? To make it more, stochastic. And this is a completely stochastic climbing game, right? Everything is stochastic, but the game is basically unchanged. And we find that the percentage of agents reaching optimal joint action, let's say AA, would be higher if we use JAL. Okay, that is, you see, this picture shows, as time goes by, right, the joint action learning performs actually better. Okay, and also we also find that when the M varies, like M is changed from 2 to 4, that is the observed agent, right? So number of observed agent is increased. Actually, the result is not changed too much. Okay, so this is how we do research in non-emergence in AI. Okay. Of course, later on we extend our work and we say, hey, how about that? We put them in some kind of network, like a small world network or scale-free network, and see what will happen. And then we find that, the best result would be in small world network with joint action learning. Okay, and this is the research we do. So you can now have a taste of what we have been doing in the non-emergence research in AI. Now, basically, we would investigate, how to improve non-emergence, and that is under what situation. Okay, how to tune the parameters so that the norm will emerge sooner rather than later. Okay, so that is one of the research themes. Okay. Now another example that I want to illustrate is, we also investigate community networks. Okay. Now in community networks, basically we assume that the agents are connected, that they are connected into different communities. So we assume that inside the communities, the members are more densely connected, but between two different communities, the members are less connected. And of course, we will characterize the community network by a parameter called separation degree. So intuitively, this is a loosely connected community network, and this is a more compact community network. And we just perform experiments and we demonstrate that when the agents would just interact according to this network topology, then this is how they will evolve, right? So for example, in this diagram, I show a typical situation in which there are 10 communities. So you will see that within each of the community, the actions taken by different agents will change, but eventually the norms will be different for each of the communities. Okay, and of course, we would try to investigate the effect of the parameters. So, for example, we consider conformity. That is, how much the agents conform to the local norms. okay, and diversity, that is, how diverse the local norms of each of the community is. So we find that, for example, the conformity we change like this. So there is basically, not much difference, because for different separation degree, they will eventually, conform to the local law. But for the diversity, you will see that for higher value of separation degree, okay, the diversity will be higher, okay. But we find that if the separation degree is smaller, like less than 0.6, then the diversity will be lower. That is basically, most of the communities will evolve to the same norm. Okay, so you see, this is one way of doing research in norm emergence. Now, the other way is that we often get insights from the real world. Okay, that is like we consider the attitudes, the social values, so whether to compromise and so on. So let me show you another example. Okay, now this is an example that of research that we have done. Okay, so in this example, we consider a multi-agent system. Of course, they will use social learning, and of course they will use the same observation mechanism as before. Okay, they will observe the different agents and agent groups. And now here we assume that the agents have, each agent is equipped with a social attitude, and when the social attitude is close to 0, the agent will be more concerned with his personal payoff. Okay, and when the social attitude is large, that's close to 1, then the agents will try to maximize the combined payoff when doing interaction. Okay, so of course, the social attitude is individualized. Each different agent will have its own social attitude. Okay, so here we say that we assume that if agents has recently earned less than other agents in interaction, then the agent will become more self-interested. And if the agents has recently earned more than other agents in interaction, then agents will try to maximize common good, right, by maximizing the combined payoff. So you can imagine that during the interaction, this agent will change its mind, right? Sometimes you are getting more selfish, sometimes you are getting more generous, pro-social and so on. So we just have this setting. Okay, and of course, this setting is inspired by the real world. Okay, so we just look at what will happen. Okay, so we just say, hey, what if the society start with everyone using the same social attitude? Okay, and then we will find that, hey, when the social attitude is basically very selfish, then there's no hope, right? Eventually, the social utility will be very low. Okay, but if initially the social attitude is very high, right, then actually it's very good. Okay, the whole society, the social utility will be very high. Okay, but if it's half and half, somewhere in the middle, including the random case, right, that is initially all the social attitudes are random, then there's a fluctuation, right, and so on. And then of course and then we consider this the changes in the average of the social attitude. We find that starting from different points, like from 0 to 0.1 up to 1, eventually the social attitude will converge to one of these 3 values. Okay, of course, all these are done experimentally, and we just collect data and we just report the result. Okay. Another research that I would like to share with you is similar. Okay, again, it is also inspired by our observation of the real world. Okay, now the setting is basically the same, right? They are all using social learning, and they are all observing a number of other agents. Okay, and then of course, again, they will play the prisoner's dilemma game. But here we assume that there exists a social value. That is, other people would think playing C is good, playing D is bad, right? This is a very common social value, right? Because even in the real world, people would think, hey, playing C is better than playing D, right? So that's a social value. Okay, now we assume that people will have a so-called perceived social value. Now, for example, for this person, okay, if most of his neighbors in the network are playing C, then he will have a high value for the perceived social value. Okay. Otherwise, if most of his neighbors are playing D, right, then the perceived social value will be low. Okay, so so this is what we mean by perceived social value. And when this agent is considering whether to play C or D, then this agent will have a social value orientation. That is, how much weight I should put on the social value. So there are two different considerations. One is, if the agent is more self-interested, then this agent should pay more attention to the actual utility that the agent will receive. Otherwise, if it is more pro-social, then this social value is more important. Of course, here we assume that the social value is unknown, but the perceived social value is what is actually used by the agents. Okay, and we find something very interesting. Okay, that is, according to the experiments, when we start with homogeneous societies, that is, everyone is using the same social value orientation, then, if initially everyone is self-interested, then eventually the percentage of norms getting a self-interested norm is 100%, right? So basically it's like this, okay? And then if initially everyone is very pro-social, then the norm emerge will be something like this, right? Very pro-social. But if the initial orientation is somewhere in between here, okay, then of course the number of norms, the percentage of norm emerge will be, like this, okay? It depends on the initial value of the social value orientation. But what is interesting is that if we look into the details here, okay, now when we say norm has emerged, then what does it mean? Now, usually people would think that, well, when norm emerges, then everything is fixed, right? Everyone is either using C or D. But actually, if we look at the details, we will find that actually everyone just keep changing his mind. Okay, so this is the X coordinate is the time, and the Y coordinates are different agents. So you see, everyone is changing his mind all the time. Okay, so it's difficult to say whether a norm has emerged or not, right? Because we have some kind of dynamic equilibrium, right, in this situation. So we also consider the dynamic society. That is, people can become more self-interested or become more pro-social according to the number of neighbors who play C or D. Okay, so for example, if everyone is playing D, everyone around you are playing D, right? So then you will become more self-interested because you think, well, no one cares about the social value. Okay, so if that's the case, then we will find that, hey, actually the average orientation will either increase or decrease, right? When the moral standard of the society is low, then eventually there's no hope right, it will go down to hell, right? Why, if the initial moral standard is high, everyone likes playing C, then actually I would just go up all the way to C, okay? And of course, we also investigate the situation, when the distribution is a normal distribution. Okay, so it's no longer true that everyone is using the same social value orientation, but they will use different thing, different values. Then we will see that the eventually the norm and merge will be different. Okay. Okay. So another another research that I would like to share with you today, okay, is that what we call competitive coordination game. Okay, that is, suppose we have a group of agents, and each of the agents would have different opinions. For example, some people would think X is better, and some other people would think Y is better. Why? Because they know that they need to coordinate. However, they want to coordinate in different ways. So for example, we assume that when the two red players are playing together and they coordinate using X, then they will both get 10, okay? Otherwise, they will get 2, right? And of course, for the green players, the situation would be different, right? If they coordinate using Y, that's better, right? Otherwise, X. And of course, one red, one green, well, that is very bad, right? Because if eventually they coordinate using X, then one gets 10, one gets 2, right? And here, 2 and 10. And similarly, we have situations like that. Now, so this is what we call competitive coordination game. And that is a very, very difficult situation. Okay, now here we say, how about that? Now it's difficult to coordinate. Now, what if we give them a third option, that is to compromise? Okay, so of course I don't ask them to compromise. They will choose to compromise if they think that compromising is a good option. Okay, so this is just an option for them, right? So CC is everyone gets 6, right? 6 and 6. Okay, so they will play this game. Now the result is this. Suppose we use random network and we use social learning and also Q learning. Okay, and then now without compromise, then we consider the situation when IAL, that's individual action learning, and joint action learning are used. And then we find that, basically there's no hope, right? Because, the result really depends on, which side is the majority, okay? If the majority, that's the proportion of agent, okay, who likes, a particular action, right? So whoever is the majority will win, okay? Just like that, okay? So if we change this 2 to 5 and to 8, then the situation is a little bit better, right? So this shows the proportion of a situation that will emerge to X or Y. Okay, so it's actually, it's better, it's not that strict. Okay, but what we want to look at is this: what is the social welfare? That is the total utility of everyone. Then we find that, in this situation, actually the social welfare is very low. Okay, and then here, when we change this to 8, then the social welfare will be increased. However, we look at the Gini index. When this is 10 to 2, then we know that, not only the social welfare is the lowest, but the Gini index is the highest. Okay, so that is really, really very bad. And then we say, what about compromise? So now we assume that they can compromise. Okay, so the result is this. Okay, so I just reproduce all the curve on the left-hand side here by representing them as dotted lines. So you see dotted lines. So all the solid lines are the results that we obtain by allowing compromises. So you see that basically, the social welfare is not changed too much. However, the Gini index is much decreased. Okay, that is, yeah, I cannot, make everyone happy, but basically, it's better for the whole society because the Gini index is lower. Okay, so these are the results. So you see, we also borrow concepts from the real world to do our research. So we have published a book, okay, on such topics. What we call, the title is Interaction in Multiagent Systems, Fairness, Social Optimality, and Individual Rationality. So of course, I would like to say that, without this title, if you only look at the subtitle, Fairness, Social Optimality, and Individual Rationality, then this book looks very much like a book in sociology, right? Okay, but here we say, no, we only talk about agents, okay? If you are from mainland China, then I would like to tell you that actually there is a domestic edition, which I promise is exactly the same as before, but the price is a lot cheaper. Okay, so you may consider buying this version. Okay, and multi-agent system interaction is a really very hot topic. So we have recently edited a volume, and we invited some of the prominent researchers from this area to write the chapters in this book, right? So if you are interested in knowing more about this research, you can consider having a look at this book, which is an edited volume. Okay, so yeah, I know I don't have too much time. So one question that everyone would ask at this moment is, for computer science, why do we want to improve norm emergence? Okay, what's the point? Okay, what do you do, right? So why? So the answer is, this is really a good question. Okay, so some wise men would say, yeah, norm is something worth investigating because, whether, for example, in real world, whether you should stand on the left side or right side of an escalator, how should you greet in different culture, or even the, how do you put the knife and forks, right? The dining etiquette. So etiquettes, so all these are interesting things, and also people would also say that in computer science they would say that this norm emergence would find applications in distributed sensor network, robot coordination, traffic control, energy management. Right? They published papers showing the usefulness of this, but for us. Let me just quote one of the most quotable quotes. That is a quotation from Mr. Spock, right? He said, in this case, I would think interesting would suffice. Okay, so we say curiosity is the key. So let me say that, just keep time and have fun, right? That is the reason why we do research in norm emergence. Okay. So let me just try to conclude the talk, right, by giving you the last topic, okay? So that is formal modeling. So far, everything has been done by agent-based simulation, okay? We would say that it would be better if we can have some kind of formal modeling, mathematical modeling, because if we have that, then we can explain the process. And it is also possible that we further develop the model theoretically, and also we can probably have some insight on the importance of different parameters. Okay, and all these cannot be obtained by purely doing research experimentally. Okay, so I'm not going to tell you the mathematical derivation, so that would be too boring and everyone will just go away. Okay, so let me just give you the idea. The idea is that we consider a society of agents. There are many agents, tends to infinity, and they are connected by random networks, and they use social learning and Q-learning. Okay, and we want to produce a graph like that. That is, the x-axis is time, and the y-axis is the changes in different key parameters, we want to produce diagrams like that by some kind of mathematical models. So the idea is that we borrow the idea of mean field from physics. Okay, in physics, when they have too many articles, no, not articles, they have too many particles. Sorry, there are too many particles. Then they will not consider the interaction between pairs of particles, right? They would just consider the mean field. Okay, so we borrow this idea, and basically the idea is that we would consider each of the agent to have a Q table like before, and there's a policy, right, if you still remember, and then we consider these Q values to be coordinates of that agents in an n-dimensional space. Okay, and we know that these Q values are kept changing, right? It changes, and therefore, we would imagine that this agent in this n-dimensional space will just move, okay, and we can write down the speed, right? And okay, I skip all the mathematical details, and I just want to show you, okay, that we find that the dynamics of the system can be depicted by some simultaneous equations like this. Okay. Okay, don't worry, I'm not going to explain all these equations. So what I want to tell you is that I just try to verify whether our results are correct. So we just use different games, okay, and we just plot the graph using the equations, and also we perform agent-based simulation, and we find that the results are the same. Okay, so it's very, very close to each other. So probably for this there are some discrepancies between the theoretical prediction and the actual experimental results. But for most of other things, most of other experiments, basically it shows that our models are correct and very accurate. So basically it means that we no longer have to rely only on agent-based simulation. We can have some mathematical models. Okay, so yeah, let me conclude today's talk, right? So just in time, I hope, right? So today, when I look at the poster of today's webinar, right? I really like this topic, when social science meet computer science. Okay, and when I see this, of course, what I have in mind is this: in social science, of course, you deal with real people. Okay, and that is very difficult, right? Because this is something that I don't know how to deal with, right? Real people, they are very complicated, and for us, for AI research in computer science, that is much easier, because in AI, you can make the agents do anything, right? You do this, and the agents will do that, right? And then we can set the environment in any way we like, okay? And that's the main difference. Now, of course, what I like most is this: social science is the answer to everything, right? So this is something that I like the most. So yeah, so that's the end of today's webinar. Okay, I hope you enjoyed it, and I hope now you have a better understanding of what we have been doing in AI, in computer science. Okay, thank you.
Yeah, thank you very much, Professor Leung, for the informative and stimulating presentation. Introduced to us different learning methods accounting for many different situations, such as joint action, compromising, competitive coordination, etc. So now the floor is open for questions.
May I start?
Yeah, sure, please.
Ho-fung, thank you for the very comprehensive introduction. A very basic question on behalf of some sociologists.
Yes.
In your framework, one of the starting point is learning mechanism. And in the standard approach, the factor approach starts with the Q learning method. In the Q learning method, there's always the concept of Q and the value Q table and so on. Now, to sociologists, how we suppose this Q to mean in reality totally change the whole meaning of a multi-agent system, such as when Q refers to money, wealth, it is one thing. When Q refers to power to override people, it means another thing. When Q refers to social popularity, or in a world of adolescence, it's about attractiveness. Wow, the logic is totally different, another world. But in the formalism that you propose, it looks like no matter what it is, you can model it the same way. So I'm wondering, by having applied this approach to try different non-emergence, can you give us a sense as an experienced user of this approach? Is it really so transcendental that you don't have to think about preconceived, say Q is money in my context. So whatever I do next have to follow this starting point. Or Q means popularity, then the whole setup of the multi-agent system would be totally different. So what is the experience about this?
Okay, that is a very good question. Thank you, Tony. So, so actually, I think I can answer this question in a way that is quite direct. Okay, so for us, we basically do not care what Q is. Q is just a value, okay, which indicates the goodness of something. So I would say this is similar to the approach used in game theory. So for example, in game theory, when you receive a utility, we just call it utility, okay? So without interpreting what this utility means in real world or in any context. Okay, so basically this is our approach. We assume that, you know, this Q value indicates how good a particular action is. Okay, and I just try to use an action that would lead me to, you know, better rewards, right, in terms of represented by the Q values. I'm not sure whether you would find this answer acceptable or not.
No, I'm not judging it. I'm trying to see whether in the modeling process. I know economists use a utility to be able to mean everything. But even economists, when they apply a certain model, they have to say this utility is mainly driven by, say, wealth, some other things. And it can affect the modeling structure. So in sociology, we care a lot about what Q is. And how we set up the system would be quite different.
Okay. So basically, you know, in our model, we assume that whenever an agent interacts with another agent, these two agents will play a game. Okay, and this game is a game in the sense of game theory, right? So that means when they play a game, that means they will receive a utility, and the agents will simply use the utility that they received by playing the game to update the Q values. So that means the Q values basically reflect the cumulated or the average utility they receive during the different interactions. So it is basically based on the utilities of the game. That's in turn depends on how you define the game that you ask them to play. Okay, so sometimes we assume that the agents are playing Prisoner's Dilemma. Sometimes we assume that they are playing some other games, right? So they just receive utilities from the games.
Thank you. I have other questions, but let others continue the dialogue first.
Okay, Serena, please.
Hi, Professor Leung. Thank you very much for your amazing lecture. And I can understand it very well, even I am not a person with business from computer science.
Oh, thank you.
Thank you. I am a drug researcher, and in drug use, some drug users in interviews, they tell me like in most cases, they relapse, they reuse drugs because they reconnect to their drug use friends. So they make a decision to use it. I think this method you introduced to us today is very promising to be applied in drug use world, like how to know their decision-making process before they choose to reuse drugs or not to reuse drugs. And they may think about, I can enjoy the euphoria from drug use, or I may be arrested by the police. So I'm curious if I want to apply this method to drug use, whether I can achieve it like totally by simulation in computer science, or I should like put this model into real world to recruit drug users to do this experiment. Then I can know the outcome or the p-value, whether they relapse or not, or the probability of relapse. I don't know whether my question is clear enough.
Yeah. Okay. So that is a very relevant question. So to answer this question, may I start with an important assumption that we have been using, okay, for our non-emergence research in AI. That is, we always assume that we do not investigate things in the real world. Okay. By making such a declaration, we avoid a lot of troubles, right? Because we don't have to say, hey, let's verify the results in the real world. Now, we never have to do that. Okay, we say, hey, that's the experiment and that's the result. If you want to verify, you just repeat the computer simulation. Okay, so that is our mentality, which is probably not very acceptable to many of you. But we always emphasize that we are doing AI instead of doing things in real world. Okay, and of course the other thing is whether your question asked is about whether our research can be applied to the situation that you have just described, the drug usage. What I would say is that if our research has to be applicable in a real world situation, then the modeling is the most important part. Okay, so how do you model their behavior? Okay, how do you model the interaction between friends? How do you model their inferences? How do you model the utilities they will get by using or not using drugs? Okay, so these are the very important things before we know whether our research can be applied in real world. But what I'm saying is, why not? Why we can try. We can adjust the parameters, or we can try different models. Okay, or we can even try to find out the correct model by interviewing them. Okay, so that is what I think probably would work.
Thank you. I got it. Thank you.
Okay. Then Li Wei, please. Oh, we cannot hear you. We cannot hear you clearly.
I think there's
no
sound at all.
Yeah.
How about this? Can you hear me?
Oh, yeah. Now, thank you.
I think this one isn't working. Thank you for your sharing. I think I appreciate your efforts because it's very difficult. I know to model social behavior. I have some questions. Because you use this agent, you try to distinguish from sociology. But I'm from political science discipline, so we study. We have principal agent model. So I wonder when you refer to agent, do you mean that in that kind of scope of literature? So then my question is, who is the principal? Because it's important when in your modeling, you assume there, first of all, the agent. Of course, some agent, they have different preferences. Some choose to collaborate, some choose not. But that model is extremely simple. I mean, and then they are, for us, individuals, they're in different organizations, they have different principles. So they're in hierarchy, for example. So and who construct these social values and who construct these social norms. So that's kind of being assumed away from my listening to your presentation. So then also, but I have some question also about your design of the experiments. Maybe I missed some your previous presentation. So I wonder when I want to apply or model to different type of policy issues, then what part of your model needs to be revised? I guess the drug issues, drug problems may be very different from like other problems like poverty. So which part of your model needs to be adjusted? And another question is, what's the implication of your research to education? Because I think the efforts of public education is trying to influence the social norms, trying to have more positive impact to change the social norms, right? So that one is maybe another conceptualization of agent. So like in social movement literature, when we talk about agent, we're trying to say someone are an agent for social changes. So I don't know how, what part of your model is trying to modeling this kind of agents, that these agents are usually minorities and their norms may be very progressive ahead of times, but they're not, may not be accepted by most people in a society. So how if that kind of agent be modeled into your model? Thank you.
Okay. So thank you. Well, you ask many questions, and I would say that many of these questions are not easy for me to answer. Okay, let me try to see whether I can answer at least some of your questions. Now, the first thing is that as I emphasized before, right? So when we did our research, okay, we never just thought about applying them in real world, because by, as I said, by declaring such a separation, okay, of our research from the real world, we avoid a lot of troubles, right? We can say, hey, we only talk about artificial societies. So in this kind of societies, things are very simple. Like for example, there are many things that we in the real world that we do not model. For example, we do not model psychology, very complicated psychology, well, in the real world, right? We don't model like rumors, fake news, or emotion. All of these are things that we can try to incorporate in the model, but we need to pay efforts. Okay, and in all these examples that I have shown you today, well, you would agree that I did not show you, right? But actually, we have tried some, right? For example, we have also we have also done some work which incorporate something like risk attitude, some adaptive behavior, So actually, I would say that everything can be done, can be incorporated into the model, as long as we have a very, very clear understanding of the concept, and the concept is so clearly understood that we can write it down formally, right? As long as this can be done, then I would say you just incorporate it into the model. Okay, so what we need is some kind of a very specific definition, instead of just some kind of definition by words. Okay, so I would say anything can be incorporated as long as you can write it down clearly. Okay, tell me what it is. Okay, so the other question that you asked was I can't remember what. So what's the second?
Related, like the concept. You said we need to define the concept clearly. Then the question about the concept of agent.
Oh yeah, the agents.
Define
Okay.
this agent.
Okay.
We have different understanding and different concept. Yeah.
Okay. So in our context, the notation for agents is very simple. Okay. So the agents would be first rational. Okay. Rational, meaning that an agent always aim at receiving higher utilities. Okay. So everything is represented by the utilities. Okay, so even when we say that some agents are pro-social, some agents are more self-interested, we also need to translate everything into utilities. Okay, and of course you can say, hey, by following the social norm or by following social value, this is the utility that you receive, and by just focus on your own interest, this is the utility that you will receive. And you will put a weight, okay, so the final utility that you receive is just a weighted sum of both, right? So you see everything is very clear and very specifically defined. So as long as you can define everything like that, then you can incorporate anything into the model. Okay, so an agent is a very, very simple notation. That is, an agent would just play games with another agent. Well, that's what we call interaction. And after interaction, it receives some utility. And then by using the utility, the Q values will be updated, right? And then the agents will try to maximize its own utility, okay, by playing, the best action, just like that.
Yeah, that's my question. Actually, sorry, Leung. Just a final comment is for those agents who want to make progressive social change, they don't follow social norms. They are not self-interested. That's, I think this is maybe different from your assumption.
Actually, today I did not give you any examples related to that. Actually, we have done something like that. But again, no, the way we did that kind of research was also based on some kind of formal modeling. So, for example, we assume that there were what we call influencer agents. Okay, those influencer agents are just very stubborn. Okay, they would not care about the loss that they will suffer. Okay, and they would just do anything they like. Okay, and even if the utility they receive is low, then they don't care, right? We assume that if there are agents like that, then how would the system be influenced, be affected? Okay, we also have done something similar to that.
Okay.
So you can see everything is based on assumption.
Yeah.
Okay. Then Wincy, please.
Hi. So Professor Leung, so now a lot of the ideas that you have looked into, now if we, in social sciences, we would be running experiments with real people.
Yes.
And for that, it's first very expensive very often, right? Because we actually have to pay people.
Mm-hmm.
And then we also have to go through IRB, right?
Yeah.
So there are things that it's ethically not possible to do. Now, do you see a possibility where your area of work can help social scientists study things where we can't possibly, perhaps due to financial reasons or due to ethical reasons, run on actual people, right?
Yes, definitely, yes. Because I think, I just said that, real people are very complicated, right? They have emotions, that they have their values, they have different, mentalities and whatever. But most of the time, I would say, people are simple, okay? Or they are simple enough to be modeled by agents. And the experiments can be can be approximated by agent-based simulation? I would say most of time, yes, right? But not always, right? So maybe at least we can use the agent-based simulation to obtain some initial results, right? And then we can verify those simulated results by some experiments with real people, right? And then we can probably revise the setting, right? So that the intelligent agents would behave in a way that is more close, right, to how real people behave. Right? This is something that can be done.
Thank you.
Okay, so any more questions? Yeah, actually, I got a question here. Nowadays, deep learning methods are very popular. So it means if we have enough observational data through surveys or through other instruments, etc., to get the observations, then can we extract the social norms, values, etc., everything? Then we can make a prediction.
Oh, this I don't know, right? Because no one has ever tried this approach, okay? And the closest thing that we have done in computer science is to use what we call deep Q learning, right, to replace the Q tables, right? So mathematically, the Q table is actually just a mathematical function, okay? That is, given any action, this function will return a value indicating how good the action is, right? And then you just keep updating this function, right? And we can represent this function in a tabular form, right? And we call it the Q table, okay? And this function can be represented by neural networks. And some people would say, I would use what we call deep Q learning. Okay, and deep Q learning is in principle similar to Q learning. The only difference is that, of course, it makes use of neural networks instead of a table. And then, of course, the updating is a little bit different, right? But the basic principles are the same. So I would say that this is the closest thing that we have done in AI. But if you say, I want to use deep learning to predict the norm that will emerge, I think, no, I'm not aware of any research work in this particular direction. Maybe the reason is that in AI, no one is really interested in this, because you see, we are not really interested in the which norm will emerge. We only want to investigate the process, and we just say, hey, we change the behaviors of the agents, and then see, and then we say, hey, let's change it and see what will happen, and let's see whether the norms will emerge sooner or later, right? Just like that. That is the main theme, and we are not particularly interested in the actual norms that will emerge. So no one has ever put any efforts in predicting, what norm will emerge.
Okay, so thank you very much. Actually, I have another question which is related to the validation of the results. It's very difficult to get the final result, but sometimes we have some partial connective behavior patterns available. Then, I mean, how can you validate your results through some partial collective patterns? Partial collective behavior patterns.
I'm not quite sure, what your question is. So what do you mean by partially connected behavior?
For example, for some communities, they may have this kind of behavior. Some other, they may have, yeah, I know that already. Because we don't know the behavior of the entire body of the people. We just know some partial behavior patterns. Then I guess these patterns can be used to validate your model in the simulations. But it may not be able to reflect the entire picture or something.
I think this is something that we have never thought about, right? So maybe you have proposed a very good research direction. Yeah. We can try to do that.
Okay.
Okay.
Yeah, thank you. So any other questions?
I think there's another question
Yeah.
chat room by Professor Qing Liang.
Qing Liang,
Oh,
please.
yeah.
So thank you, Professor Leung. My question is relating to your norm emergence methodology. The question is, so how do you model this? Well, in economics, we call that equilibrium, right? So in your case, it's the emergence. So how do you model this? Or, I mean, how do we know there is the emergence or the equilibrium?
Oh, okay,
Because sometimes the game theory, if you do not have, for example, this dominant strategy or equilibrium, it could have several. Well, from the optimization perspective, it could have several local equilibrium, not the global one. So I'm curious about this in your modeling. So that's the first question. The second one is about the dynamics, which is quite exciting, but also how. So, for example, in the economic system, there sometimes are random shocks, right? For example, due to the COVID-19 or because of the oil price crisis. So I mean, is your model allow for those change of regimes that eventually will also affect the final outcome of this agent modeling? Thank you.
Okay. Thank you for the question. Now, these questions are very technical. So let me try to answer the first question. The first question is about equilibrium. So I think that in principle, we really do not care too much about the equilibrium, right? So of course, you can say that for most of the games there are a Nash equilibria, like, or even if for games without pure strategy Nash equilibria, there are always a mixed strategy equilibria. But for non-emergence, we don't really care about what the correspondence between the norm and the equilibrium. So we only say that, well, if the norm emerges, then it emerges, and that is it, right? And we only require 90%. Okay, of course, 90% is an arbitrary number. So we only require that, but as long as 90% of the agents take the same action, then we say that norm has already emerged, and that is it. And whether or not that is the equilibrium, I think not too many people are interested in it, right? So if it is a equilibrium, then it is an equilibrium. If it's not, then it's fine. It doesn't matter. Okay, that is our approach. Okay, so of course, some people work on more theoretical aspect. Then they will say, hey, we can prove by theorem that if you follow this procedure, then eventually after some time, a norm will emerge, and that norm should correspond to a particular Nash equilibrium. Of course, there are results like that, but people would normally consider this kind of results to be some interesting results, but they are interesting, but not very not always the main result. Okay, they are interesting results. So I hope that this would answer your first question, right? So in summary, the question. The answer is we don't really care about equilibrium, right? Because if the norm emerges, then it emerges, and if it is an equilibrium, that's good. Otherwise, it's still okay, right? It doesn't matter. And then the second question is, do we allow some kind of dynamic changes, like sudden changes, like something all of a sudden something happens? Then we say, yeah, of course, why not, right? Because we just do computer simulation, right? In computer simulation, you can do anything you like, right? You just change the program and then say, hey, after this, suddenly half of the people leave the system, right? This can be done, right? By computer simulation, and that's pretty easy. So I'm not sure whether I answer your questions.
Oh, yes, thank you very much.
Okay. Then Sunny, do you want to ask question yourself? There is a question appear in the chat window.
Let me see. Sunny. Okay.
Yeah.
So you have mentioned some methods for non-emergence research. I would like to know that which is the most common method for algorithm in each research common method. I'm not quite sure what you mean by method or algorithm. So basically, we don't have any particular specific method or algorithm because we don't really need any method or algorithm. We just implement everything using very simple computer programs. So in terms of computer programming, our programs are usually very, very simple. Okay, it's not complicated. As you can see, we just say we only need to implement Q-learning, and Q-learning is quite straightforward in terms of implementation. Okay, so all we need to care when we really do coding is to make sure that the coding is efficient so that it does not take too long to complete the simulation.
I want to follow up on that. I want to ask a follow-up question on that. So even though the Q-learning itself, it's quite simple, right? But let's say if we want to use deep Q-learning, the computational power required would be quite substantial, right?
Yeah, that's true.
Start doing it at all would require quite a bit of investment, either by the researcher or by the department, right?
Yeah.
And is that worth making, or what would you think on this?
Of course, in computer science department, we don't consider that to be a problem, right? Because we have machines, right? So
right.
Okay. So for example, I have recently spent like 800,000. Yeah, is it 800? Yeah. So how much was it? Yeah, just so something like no, not 800. So $100,000, right, to buy a computer, right, with GPU and so on. Okay, and it will be put in my own office. So you see, we are quite okay with equipment. So of course, we always say that we are not very environmentally friendly because we use too much electricity, right? So that's the main problem. So investment, yes. So anything that involves computer would have implication in terms of investment, money, right? That's very important. That's very important.
But for social scientists, like which have different budget constraints, right? Would you advise like we act like computer scientists when we buy computer equipment, or you think there are like more low-hanging fruits where we can do it cheap?
Well, this is not a question that I can answer, right? You can ask Professor Tam and Professor Huang, right? And they would have better answers.
Thank you.
Okay.
Okay, so in the interest of time, I guess we should stop here. And before that, I would like to thank Professor Leung for your very insightful presentation and all the audience for your active participation. And next month, we will have another talk to be given by David Laza. Okay, so another, important figure in the field of computational social science. I hope to see you then. So thank you very much.
Okay, thank you.
Thank you. Ho-fung.
Thank you.
Thank you.